All right, so let's say that we have an electric charge that exists within some electric field E. How do we move it? If we move this charge Q around within the field, how much work does it take to move it? And what force do we have to exert on this charge in order to move it? We already know that the electric field is going to exert a force on the charge. So there's going to be Fe, which is equal to Q times the electric field, right? So if we wanted to move it in our own direction that is not the direction that the force is moving it, then we're going to have to exert a different force. I'm going to name it F move like that, which is going to have to be minus Fe because we have to move it against the electric field. And in that case, the amount of work that we do to this charge is going to be the integral from wherever we start to wherever we end of the force it took to move the charge dot dl. Okay. That force, the force it took to move the charge, was minus Fe, right? Because we said that down here. So that is equal to minus the integral from A to B of the force due to the electric field dot dl. Okay. And then once we have put it at whatever location, we're going to write that as WAB, the work that it took to get from A to B. And then whenever we put it at B, that charge now has potential energy associated with that positioning. Well, what if we divide this by Q? Let's take the whole thing, divide it by Q, divide that by Q. Suddenly we have the voltage. So the voltage between point A and point B is minus the integral from A to B of the force due to the electric field was QE. So that's just E dot dl, which is the work it takes to move from A to B divided by the charge. So you can think of this as the potential energy per unit charge that is associated with being at point B with reference to point A. Voltages always have to be referenced to something. You can't just have a voltage that is global. My voltage is not 5 volts. It's always got to be referenced to something. So if you don't know where ground is, if you don't know where your 0 volts are, then that means nothing. And really you could say that ground is actually ground is 1,000 volts today instead of 0 volts. And that would be okay because we don't care what number you assign to ground. As long as you have a value and a location, you're good. So I wanted to talk about voltage today because we're talking about circuit principles and path laws and how these things are associated with each other. And we're going to talk today about Kirchhoff's voltage law and where it comes from. We're going to spend more time on a specific one of Maxwell's equations in the next chapter, but I want to introduce you now to Faraday's law. Which is that the curl of the electric field is equal to minus the time derivative of the magnetic flux density. This might not seem like it means anything to you now, but take the integral of this over a surface, an open surface, not a closed surface. Let me do that over a surface and do that over a surface, right? I'm gonna do a little ds there and a little ds there. On this side, I can apply Stokes' theorem. And when I do that, the result is that the line integral of the electric field around the boundary of that surface, a closed path, is equal to minus the time derivative of the magnetic flux through the surface. We're not talking about the time derivative of the magnetic flux today. What we're going to talk about is the electrostatic situation where this time derivative is 0. And now what we have is that the integral of the electric flux of the electric field around a closed loop is 0. And we also have that the voltage is minus the integral of E dot dl. If you want to talk about the voltage between 2 points, whoops, that's BA, AB. These are the 2 ingredients of Kirchhoff's voltage law. And now I want to pause and have a little discussion about that.